Ever get the feeling that, like, the most mind-bending math ideas, like the ones that practically seem like they were invented to just give us a headache, somehow end up, like, revealing something incredibly elegant about the universe?
Mm-hmm.
Well, buckle up, because today's deep dive is going to be a wild ride into advanced mathematics, and trust me, the destination is well worth the trip.
I'm sure it is.
We're diving headfirst into a paper by RUBEN A. HIDALGO called Get Ready for It. A simple remark on holomorphic maps on Torelli space of marked spheres.
Wow.
Now, I'll admit the title alone might make you want to reach for a dictionary or maybe a stiff drink, but I've got a feeling you're going to help us untangle this mathematical knot and uncover the elegance within.
I can assure you the journey is well worth it.
Mm.
Hidalgo tackles a fascinating problem here, and the way he unravels it is surprisingly intuitive, even if the terminology might sound a bit intimidating at first.
Speaking of intimidating, maybe we should start with something a little less tongue-twisting, like this whole marked spheres business. What are we even talking about when we say a sphere is marked, and what makes that mathematically interesting?
It's all about understanding the relationships between points.
Okay.
Imagine taking a sphere, your average everyday sphere, and we strategically place a few points on its surface. These are our marks.
Okay.
Now imagine we have a whole bunch of these marked spheres, each with points sprinkled across them in different arrangements. The question becomes, how can we understand the relationships between these different configurations? How do we map out the connections, the transformations, the underlying structure that connects them? That's where this idea of Torelli spaces comes into play.
Okay, so it's like we're trying to find a way to organize and categorize all the possible ways you could arrange those points on the spheres. We're creating a system to make sense of the chaos, right?
Precisely. Torelli spaces give us that system. They allow us to group similar configurations together and study their properties. In this paper, you'll see them represented by the notation U sub 0, comma k plus 1.
And I'm guessing that k is hiding some crucial information.
You bet it is. The K represents the number of marked points we're dealing with beyond the initial 3, which are always present on our spheres.
It's just like each sphere has a VIP section with 3 guaranteed spots, and then we can invite K more points to the party, depending on how lively we want things to get.
That's a fun way to put it. And that subscript 0 you see in the notation, that tells us the genus, which in this case being 0, means we're sticking with the simplicity of spheres for this deep dive.
All right, so no donut shapes for us this time. But back to these marked spheres for a second. To really grasp what Hidalgo is doing with them, we need to talk about the Riemann sphere, right? That's where this whole idea of marking a sphere starts to get really interesting.
Exactly. Think of it this way. The Riemann sphere is like a mathematician's playground. It's a way to visualize the entire complex plane with all those real and imaginary numbers as a single continuous surface.
Hold on. We're taking something as vast and mind-boggling as the complex plane and somehow wrapping it all up into a neat little sphere. That sounds like some serious mathematical origami. How does that even work?
Picture a flat sheet stretching out infinitely in all directions.
Okay.
That's our complex plane. Now imagine taking that sheet and carefully tucking the edges up and around, bringing them together at a single point infinitely far away. What you end up with is a sphere. And that, my friend, is the ingenious concept of the Riemann sphere. It's like we've taken something infinitely vast and compressed it into something finite and manageable.
So it's kind of like those old maps of the world where they squeeze the entire globe onto a flat surface. It distorts things a bit, but gives you a different perspective.
Exactly. And just like those maps, the Riemann sphere lets us visualize things in a way that makes certain mathematical operations much easier to work with. It's a powerful tool, and it's crucial for understanding what Hidalgo is doing with these marked spheres.
Okay, I'm starting to see why this Riemann sphere is such a big deal, but how does it tie back to those marked points we were talking about? How do those markings fit into this whole spherical puzzle?
That's where things start to get even more interesting. You see, when we talk about marked spheres in the context of the Riemann sphere, we're not just talking about any random points. We're talking about specific points that represent complex numbers on this spherical surface. Each mark is like a coordinate, a specific location on our complex plane, now elegantly represented on the Riemann sphere.
So it's like each marked point is a tiny piece of information, a complex number, carefully pinned to a specific spot on this sphere.
You got it. And the way these points relate to each other, their distances, their configurations, the patterns they form, That's where the real magic starts to happen.
All right, so we've got these marked up spheres, each one a tiny constellation of complex numbers on the surface of the Riemann sphere. But where do we even begin to untangle the relationships between them? How does Hidalgo even approach this problem?
That's where the concept of holomorphic maps comes in. These are the tools that allow us to navigate between different configurations of our marked spheres.
So are we talking about something like those maps you see in fantasy novels where one world folds into another? Are we about to jump through a portal into a different mathematical dimension?
Not quite, but I love the enthusiasm. In a way, holomorphic maps are kind of like mathematical portals. They take us from one Torelli space to another, but instead of transporting us physically, they transform these marked spheres in a way that preserves their essential geometric properties.
Okay, so it's more like a set of rules for reshaping and transforming these spheres, but always in a way that makes sense mathematically. We're not just randomly shuffling points around, are we?
You're exactly right. Hidalgo is particularly interested in a special type of holomorphic map called a non-constant holomorphic map. These are the rule breakers, the ones that can actually change the number of points on our spheres as they work their magic.
Oh, now that sounds interesting. We're not just talking about rearranging the furniture. We're talking about adding or removing pieces altogether.
You've got it. And what Hidalgo discovered about these non-constant holomorphic maps is where things get really mind-blowing. He found that every single one of these complex transformations, no matter how intricate they might seem, can be broken down into two fundamental operations. It's like discovering the basic building blocks of a complex dance move. All right, you've got me on the edge of my seat. What are these two fundamental operations? Tell me everything. The first one he calls an automorphism. Think of it like rearranging the books on your bookshelf. You're not changing the number of books, just their order. Similarly, an automorphism rearranges the marked points on the same sphere, creating a new configuration within the same space.
Okay, that's pretty intuitive. So what's the second operation, the one that lets us change the number of points?
That one is called a forgetful map, and it's essentially as straightforward as it sounds. It's like taking a few books off your shelf altogether. You're left with fewer points to consider effectively mapping our sphere onto a Torelli space with a different k value.
So we've got our rearrange move with the automorphism and our move with the forgetful map. And Hidalgo is saying that every single non-constant holomorphic map, no matter how wild, is just some combination of these two basic actions. That seems almost too simple. What am I missing here?
What's remarkable is that he doesn't just make this claim, he proves it. And the way he does it is where the true beauty of his work shines through. He uses a concept called the cross ratio to demonstrate this elegant truth.
Cross ratio. Now, there's a term I haven't heard in a while. Give me a refresher. It's not as scary as it sounds, right?
Not at all. A cross ratio is a way to describe the relative positions of 4 points on a line or a circle. Imagine drawing a line through 4 points, A, B, C, and D. The cross ratio of these points is a specific mathematical relationship between their distances captured by this formula. Open parenthesis D minus B, close parenthesis, open parenthesis C minus a close parenthesis, divided by open parenthesis D minus a close parenthesis, open parenthesis C minus B, close parenthesis.
Okay. I vaguely remember that formula from somewhere in the depths of my math education. But how does this seemingly simple formula tie into the mind-bending world of holomorphic maps and marked spheres? It feels like we've gone from advanced calculus to high school geometry in the blink of an eye.
And that's the beauty of Hidalgo's discovery. He found a way to bridge these seemingly disparate areas of math and reveal a hidden connection. He proved that every coordinate of a non-constant holomorphic map between these Torelli spaces, every single aspect of those complex transformations can be expressed as a cross ratio of the marked points on our spheres.
Wait, hold on. Let me make sure I'm wrapping my head around this. You're saying that this one elegant formula, the cross ratio, is like the secret code that unlocks the entire system. It governs the fundamental geometry of how these maps work. That's kind of amazing.
It is amazing. Hidalgo found the hidden elegance within this complex mathematical structure. It's like finding out that the intricate movements of a clock are all driven by a few simple gears working in perfect harmony.
So we've gone from these elaborate holomorphic maps and Torelli spaces to this unexpectedly simple formula for the cross ratio. It's like we've stumbled upon a hidden doorway leading to a deeper level of understanding.
That's a great way to put it. Hidalgo's work is all about uncovering those hidden connections, revealing the elegant machinery beneath the surface complexity.
And to think this entire time we've been talking about spheres, those perfectly symmetrical objects we all know from geometry class, It's amazing to think that there are still hidden depths to explore, even in something as seemingly familiar as a sphere.
Absolutely, and that's one of the most exciting aspects of this paper. It opens up new avenues for exploration. Hidalgo's work primarily focuses on genus 0, those spherical surfaces, but his findings hint at the possibility of similar elegant relationships existing in higher genus spaces like those donut-shaped objects we mentioned earlier.
So we might be able to apply the same kind of cross-ratio analysis to understand complex mappings on completely different shapes. That's fascinating. It feels like we're only just beginning to scratch the surface of what might be possible.
Exactly. What if those seemingly complex maps on higher dimensional shape structures with even more twists and turns also boil down to a handful of elegant operations, all governed by some surprisingly simple geometric principle?
It's like realizing that the entire universe might be orchestrated by a few fundamental laws waiting for us to decipher them.
Precisely. And who knows, maybe one day someone will look back at Hidalgo's work as the key that unlocked a whole new understanding of higher dimensional mathematics.
Well, you've certainly given us a lot to ponder today. Who knew that a deep dive into complex manifolds could leave us feeling so energized, from the Riemann sphere to Torelli spaces and the unexpected elegance of the cross ratio? It's been an incredible journey. Thanks for guiding us through this fascinating world.
My pleasure. Always happy to share the wonders of mathematics.
And for those of you listening, we hope you've enjoyed this deep dive into the world of advanced math. Until next time, keep those minds curious, and remember, sometimes the most complex problems lead to the most elegant solutions.
All right, so you said this paper our way, holomorphic maps on Torelli space of marked spheres.
I gotta say, that title sounds a little intimidating, not gonna lie.
Yeah, it's a mouthful.
What's the core idea in plain English?
So at its heart, it's about visualizing and understanding relationships.
Okay.
Think of it like trying to map out connections in a network.
Okay.
But not just for like one setup, but for every possible configuration of those connections.
So instead of just like internet connections right now, we're
Yeah.
talking about like all possible internet connections ever.
You're getting warmer, yeah.
Okay.
That's where Torelli space comes in.
Okay.
It's like a map. But instead of physical locations, it shows where all potential network relationships could exist.
So if I'm picturing a map with like dots for cities and lines for roads,
Right.
Torelli space is more like all the potential cities and roads, even the ones that haven't been built yet.
Exactly. And this paper focuses on holomorphic maps between these Torelli spaces.
Think of them like special maps that preserve the structure of those relationships, even if they simplify things a bit.
So like how a world map stretches out Greenland,
Mm-hmm.
but the continent's positions are still accurate.
Yeah, a great way to put it.
Yeah.
And these holomorphic maps can't just be anything goes. There are rules.
Rules. I love rules. Makes it seem more manageable. What kind of rules are we talking about?
One of the big findings, they call it theorem 1. You can't just map a more complex Torelli space onto a simpler one
Okay.
without losing information. Like cramming a 4K movie into a tiny low-res format.
Something's got to give.
Exactly.
Yeah.
Another rule is that these maps use something called cross ratios.
Cross ratios.
Imagine dots on a map representing network points. A cross ratio measures the relative positions of those points, quantifying the relationship between them, not just their locations.
So it's not just where they are, but their arrangement and spacing relative to each other.
Exactly. And get this, the paper gives a blueprint for building these maps. They use permutations, rearranging those points, and projections, mapping them onto different spaces.
So they didn't just discover these rules, they figured out how to use them to build these maps. That's impressive. But I have to ask, why does this matter? What's the practical application of mapping these Torelli spaces?
It might seem abstract, but it has implications for fields you might not expect. Like that map analogy, these tools help us make sense of complex systems.
You could give me some concrete examples.
Mm-hmm.
Where do these Torelli spaces and holomorphic maps actually show up? Outside of a mathematician's notebook, I mean.
Well, one area is physics string theory.
So,
Physicists are using these mathematical maps to try and understand the very fabric of the universe, the relationship between dimensions we can perceive and those we can't even imagine.
from maps to the structure of the universe, that's pretty out there. But I see what you mean. If you're dealing with things like extra dimensions, having a way to visualize those relationships must be valuable, even if it's abstract.
It's like trying to draw a map of a city, but you can only see in 2 dimensions.
Okay.
You know, there are tunnels and skyscrapers above you. These tools give us a way to at least start sketching out those hidden connections.
That's a great analogy. And it's not just physics, right? You mentioned other fields too.
Absolutely. Data analysis.
Okay.
We're dealing with huge data sets. These types of maps can help us find hidden patterns in that data, leading to new insights in fields like medicine, finance, even social sciences.
So if you had all the interactions on a social media platform, these maps can help you understand how information spreads or identify influencers.
It's more complicated than that, but you're on the right track. By understanding how to map and simplify these relationships without losing information, we can develop better algorithms and tools for making sense of big data.
Okay, I'm seeing how this math can have real-world uses. But there was something else in the paper. Riemann surfaces popped up. What's the connection?
Ah, yes. This is interesting. Remember how we talked about holomorphic maps needing to follow rules?
Right.
The paper connects these maps, these Torelli spaces, and Riemann surfaces.
Riemann surfaces. It has something to do with topology, right? Like a coffee cup and a donut are the same shape if you're only looking at their surfaces.
Exactly. A Riemann surface is kind of like that. It takes a flat plane and twists it, stretches it, creating these shapes that are still mathematically consistent.
Okay, like those Mobius strips.
Yes. And the paper uses a famous theorem called the Picard theorem. It talks about the limits of what holomorphic maps can do on Riemann surfaces.
Limits. So even with twisted surfaces and complex mapping, there are still rules.
Precisely. And the researchers showed how this theorem, which applies to Riemann surfaces, also has implications for the maps they're studying on Torelli spaces. That's a big deal.
Okay, I'm trying to wrap my head around all this. We've got these abstract Torelli spaces, holomorphic maps with their own rules, and now we're connecting these rules to topology and Riemann surfaces. It's a lot.
That's what's exciting about this paper. It's not just about these mathematical objects, it's about the connections between them.
Speaking of connections, the paper didn't just lay out these abstract ideas. They provided tools for working with them, explicit models for Torelli spaces. It sounds like going from theory to practice.
You're right, that's crucial. They realized to make their findings useful, they needed to provide a way to actually work with these concepts. So they developed these models, basically mathematical formulas, that allow you to calculate and experiment with different scenarios.
So instead of just saying, here's this concept, they said, here, go play with it, see what you discover.
Exactly. They provide examples. Starting simply with a few points on those maps, showing how the formulas work, then they increase the complexity, adding more points, demonstrating how the principles still hold true.
That's a good way to approach it. Start with a foundation, then build on it.
And they go further. They demonstrate how the symmetries of these spaces, the ways you can transform them without changing their properties, how those symmetries change as you add more points.
So each new point, each new connection creates a ripple effect, revealing new complexity.
Precisely. And that's where this research leaves us. They've given us these tools, these maps and models, and now it's up to mathematicians to see what they can discover.
It's like they've handed us a map to a new continent and said, go explore.
And who knows, those discoveries might lead to breakthroughs in fields we haven't even imagined yet.
It really makes you realize that even though this is advanced math, it's not just about numbers. It's about pushing the boundaries of what we know. Speaking of understanding, there was one thing that struck me as I was going through this paper. For all the talk of spaces and equations, there's something visual about this paper. Like I kept picturing those spheres and those lines connecting relationships.
That's interesting. You've hit upon something about math. We use equations and symbols,
Right.
but those represent deeper concepts, and those concepts often have a geometric side, even if we can't visualize them directly.
It's like those optical illusions where you see depth on a flat surface.
Yeah.
But here it's like the math hints at something even more complex than our brains can grasp.
It's like we're getting glimpses into higher dimensions through math.
So even if I don't get all the details about holomorphic maps and Torelli spaces, I'm taking away that this research is about pushing the boundaries of what we can know.
Exactly. And that drive to understand is what makes math so compelling. It's not always about practical uses. It's about knowledge.
It's like that quote, the more I learn, the more I realize how much I don't know. This paper is like that. It gives answers, but also opens up new questions.
Exactly. It sparks curiosity. It makes mathematicians want to explore further.
So for our listeners who are feeling that spark, but maybe also a little overwhelmed, any final thoughts?
Think about the maps you see every day. And I don't mean Google Maps, I mean metaphorical maps. The ways we understand the world.
Give us an example.
A musical score. It's a map representing sounds and rhythms relationships between notes. Or a recipe. It's a map guiding you through a process.
Wow, maps are everywhere. And they're not just about location, but about showing a structure and relationship.
Exactly. And this paper shows us that even in abstract math, there's beauty and elegance to these maps. And maybe by studying them, we'll understand more than just the cosmos, but ourselves too.
A universe that might just be a reflection of the equations and structures behind it all.
On that note, I think we'll wrap up this deep dive. Thank you for joining us today.
It was my pleasure. Hey everyone, ready to dive into something fascinating. Today we're going to be exploring advanced mathematics, specifically Torelli spaces. And don't worry, we'll make it understandable.
Sounds like a plan.
Our guide for this adventure is this really interesting research paper by RUBEN A. HIDALGO. I'll be honest, I had to put my thinking cap on for this one. Luckily, our expert here can break it down for us. So, what are Torelli spaces? Think of a sphere, like a globe. Now imagine we poke a few points on it.
Like push pins on a map?
Exactly. Those are our marked points.
Yeah.
We're not just randomly scattering them, though. The Torelli space is like a giant catalog that maps out all the fundamentally different ways you can arrange those marked points on the sphere.
It's about understanding the relationships between those points.
Now, you might be wondering why this even matters, right? Why care about points on a sphere? Well, this actually connects to some pretty big questions about, like, how we understand the universe itself, things like the configuration of particles in physics or even complex networks in computer science.
It's all connected.
It is. So we've got these marked points defining our Torelli space, but what makes their arrangement so important?
Well, this Torelli space isn't just some vague idea. It has a very specific structure in mathematics. We call it a complex manifold.
Manifold. Okay, now I'm feeling a little lost.
Imagine you're trying to map the Earth, right? If you look up close, it seems flat, but zoom out and you see the curvature. Complex manifolds are similar. Up close, they look like a flat plane of numbers, but the overall structure can be much more intricate.
Okay, so our Torelli space, this catalog of marked points, has hidden layers of complexity depending on how we look at it.
You got it.
So more points, more dimensions, more complexity. But we're not done yet, are we? Now we're going to throw in something called holomorphic maps.
Ah, yes, holomorphic maps. Think of it like stretching a rubber sheet. You can distort it, pull it around, but you can't tear it or fold it onto itself. Holomorphic maps are kind of like that. They're special transformations that let us manipulate those complex spaces without breaking their structure.
So like rules mathematicians have to follow when playing around with these abstract spaces. No cheating allowed.
Exactly. They let us stretch and rearrange, but we can't just rip holes in our mathematical fabric, right? And it turns out these holomorphic maps are really important for figuring out the relationships and symmetries that are kind of hidden within these Torelli spaces.
Okay, so they're like tools that let us play around with these spaces and see how they work without breaking them.
Yeah, good analogy. And what's really cool is what happens when we use these holomorphic maps on our sphere with those marked points. This is where RUBEN HIDALGO's research comes in.
Oh, yeah. I've been wondering about that HIDALGO's theorem. What's that all about?
It's actually kind of a surprising discovery. See, it turns out there's a limit to what these holomorphic maps can do. You can't just create new marked points out of thin air. It's like you've got this rule that says you can move the points around, but you can't just add more of them.
So I can't magically make more points appear with these maps.
Nope, you're stuck with the ones you start with. And that's a pretty big deal because it means there's a constraint on how information, which is represented by those marked points, can be transferred between these Torelli spaces when we're using these holomorphic maps.
So it's less like making copies and more like just rearranging what's already there.
Right. You can only keep things the same or maybe get rid of some information, but you can't create anything fundamentally new.
Interesting. So how do these holomorphic maps actually forget points? What's going on there?
Well, that's where we need another tool from our mathematical toolkit. It's called a cross ratio.
Cross ratio.
What's that?
Imagine you have 4 people sitting around a table. The cross ratio is basically a way to describe their positions relative to each other, no matter how they move around the table. It's all about the relationships.
So it's like a way to capture the arrangement of those people without worrying about the specific places they're sitting.
You got it. And what HIDALGO found is that any holomorphic map between these Torelli spaces can be completely understood by just looking how it changes those cross ratios. So we're not creating or deleting points. We're just kind of shuffling them around, changing their relationships.
Exactly. And this connection to cross ratios is super interesting because it links Hidalgo's work on Torelli spaces to a bigger idea in math, a conjecture about something called Teichmüller spaces.
Teichmüller spaces. Now, those sound even more complicated.
They are a bit, but the gist is that mathematicians have this hunch that certain maps between Teichmüller spaces are also what we call forgetful maps. They can only keep or discard information, just like these holomorphic maps we've been talking about with Torelli spaces.
So it's like we're finding these unexpected connections between different parts of math. Almost like everything's linked together somehow.
Yeah.
It really makes you wonder what other hidden connections are out there just waiting to be found.
Exactly. And that's what's so exciting about math. We keep uncovering these links between things that seem totally different at first glance. Hidalgo's work is a perfect example. He's showing us something really fundamental about these complex spaces and how we can work with them. But he's also hinting at a much bigger picture, something that connects these ideas to a whole bunch of other areas in math.
It's like we're putting together a giant jigsaw puzzle.
Right. And the best part is we've only just started to put the pieces together. Remember how we talked about trying to visualize those Torelli spaces? We use the donut analogy for a 2D space. But Hidalgo's paper actually deals with spaces that have way more dimensions.
Yeah, those are a little harder to imagine.
To say the least. It's a real challenge, even for mathematicians, to wrap their heads around spaces with more than 3 dimensions. It kind of breaks our brains a little bit.
It's amazing, though, that even without being able to picture these things, math gives us the tools to understand them.
Exactly. It's like we're developing new senses. You might not be able to see those higher dimensions with your eyes, but through math, you can start to feel them out, understand how they work.
It's pretty mind-blowing when you think about it.
It really is. And honestly, we're just scratching the surface here. There's still so much more to discover about these spaces and how they connect to everything else.
Well, I think that's a good place to stop for today. My brain needs a break after all that high-dimensional thinking.
Mine too. But that's the thing about math, it kind of sticks with you. You start seeing those patterns and connections everywhere.
So true. Well, listeners, we hope you enjoyed this deep dive into the world of Torelli spaces and holomorphic maps. Remember, even if math isn't your thing, there's something really beautiful about the way it helps us understand the universe.
Couldn't agree more.
Until next time, keep exploring. Keep those questions coming. And remember, the most amazing discoveries are often just a deep dive away. Welcome back, math fans. Today we're taking a deep dive into something called Torelli spaces. I know, it sounds kind of intimidating, but trust me, it's like a cosmic game of connect the dots.
That's a great way to put it. We're essentially talking about the geometry of how we arrange points.
Right. Imagine you have a bunch of points, and the Torelli space is like a map of all the different ways you can arrange them. It's like a blueprint for all possible constellations, but instead of stars, we're dealing with points.
Exactly. And the paper we're looking at today focuses on a specific type of Torelli space, one that deals with these things called marked spheres.
Okay, now those spheres aren't your typical basketballs, right? This is where the complex plane comes in.
You got it. Think of it like a map on your phone, but one that stretches out infinitely in all directions. You can zoom out forever and you'll never hit an edge. That's the complex plane, and those marked points are like points plotted on that infinite map.
So instead of stars in the sky, we're talking about points scattered across this infinite map. But how do we even begin to wrap our heads around all the different ways to arrange those points? The possibilities seem endless.
You're right, it could get pretty overwhelming. That's where these handy tools called Mobius transformations come in.
Mobius transformations. Sounds complicated.
It's not as scary as it sounds. Imagine taking that infinite map and stretching it like a rubber sheet. Twisting it, zooming in or out, Mobius transformations. Let us do all of that without ripping or folding the map. And we use them to rearrange our points in a standardized way.
So it's kind of like finding a way to line up all those constellations in a certain order, even though they're scattered across this infinite map.
Exactly. And once we've got our points organized, we need a way to categorize these different arrangements. That's where these two concepts come into play. Teichmüller and moduli spaces.
More spaces. Okay, I'm ready for another brain stretch. Give me the breakdown.
Think of them both like families or collections of infinite maps with points on them. But here's the catch. Teichmüller space is like that super organized friend who remembers exactly where you put things. It cares about the order you put those points on your map. Moduli space, on the other hand, is more laid back. It only cares about the overall picture, not the order you connected the dots.
Got it. So Teichmüller space is like a numbered list, while moduli space is a picture without numbers. But where does this Torelli space we're focusing on fit into all of this?
Good question. Just like Teichmüller space, Torelli space is very particular about the order in which we place our points. It's not just about where they are, but also the sequence in which they were placed on our infinite map.
Okay, so going back to our constellations, it's like we're not just looking at the pattern of stars, but also remembering exactly how we connected them to create that pattern. And this seemingly small detail, remembering the order, is what makes Torelli spaces so fascinating and complex. And this brings us to the work of RUBEN A. HIDALGO, and this paper we're diving into. So we've got these infinite maps, and we're carefully remembering the order we put the points on them.
Yeah.
What exactly does HIDALGO's research tell us about these Torelli spaces?
Well, one of the things that's really interesting is that he looks at functions between these spaces.
Okay.
So ways of taking one arrangement of points and transforming it into another, all while staying on that infinite map.
Okay, so like transforming one constellation into a different constellation, but with these points on a complex plane.
Yeah.
So HIDALGO found something interesting about these transformations.
Yeah, so imagine you've got two of these maps, two of these infinite maps, and they've got these different arrangements of points marked on them. What HIDALGO found is that anytime you have a function that smoothly maps the points from the first map to the second map, like no matter how complicated that function might seem, you can always break it down into two simpler steps.
Okay, that kind of sounds like a magic trick. Take something really complicated and make it simple. So what are the two steps?
So the first step might involve what we call a forgetful map, and it's basically where we just ignore some of the points on the first map.
Okay, so we're being a little picky.
Yeah. So
We're only paying attention to certain points. What about the second step?
So that's where these Mobius transformations that we were talking about earlier come into play, the stretching and the twisting.
Right.
So after we've potentially forgotten some of these points, we then use a Mobius transformation to manipulate that first map, and we stretch it, we twist it, until the remaining points line up perfectly with their counterparts on that second map.
So it's like a two-step dance. Forget some of the points and then stretch and twist to make the others match up. That's pretty cool. I'm starting to see why you called this elegant earlier. But why is this two-step process such a big deal in this world of Torelli spaces?
Well, it's a big deal because it shows us that there's actually a structure within these spaces that we didn't know about before, right?
Okay.
We're saying that even though there are infinite ways to arrange those points, there's an underlying order to how we can transform from one to the other.
So even in this world of infinite possibilities, there are still rules, still patterns waiting to be discovered.
Exactly.
Does HIDALGO give us any concrete examples of how this works?
He does, yeah. He dives into a really specific case in section 2.4.4 of the paper, and he uses permutations, so think of those like ordered lists of our points,
Okay.
to really clearly show how this forget and transform process plays out. It's like he's walking us through a step-by-step guide for how to morph one point arrangement into another.
It's always nice to have that, hold on to that concrete example. But this idea, this hidden order that he found, it's not just about Torelli spaces, is it?
You're right. It actually connects to this bigger question that mathematicians have been thinking about, and it has to do with Teichmüller spaces.
Right, the numbered list.
Exactly. And there's this conjecture, you can almost think of it like an educated guess in math, that there's a similar forget then transform principle that might also be happening in Teichmüller spaces. And so HIDALGO's work is giving even more evidence to support that conjecture, which is a big deal because it could be a step towards solving this mathematical mystery.
So it's almost like his work with these kind of flat, infinite maps could unlock an understanding of these even more intricate spaces, these Teichmüller spaces.
And what's even more intriguing is this idea of a hidden order, right? This hidden structure. It connects to something much more simple called cross ratios.
Okay, cross ratios. I kind of remember those from high school geometry. But how do those fit into this world of infinite maps and all these transformations?
Don't worry, it's actually a pretty simple idea. Just picture 4 points all lined up like markers on a ruler, and there's this number we can calculate called the cross ratio, and it basically tells us the spacing pattern between those markers.
Okay, so it's capturing the relationship, like a mathematical snapshot of those points on the ruler.
Exactly. And here's the really cool part. Even if we move those markers around, as long as that cross ratio stays the same, we know that they're connected in that special way. It's like the secret code between their positions, even if they're not in the same place anymore.
Okay, that's really cool. But we're not talking about points on a ruler, are we? We're talking about these infinite maps and these transformations. How do cross ratios play into all of that?
Well, this is where Hidalgo's discovery gets really mind-blowing. So remember these functions we talked about, the ones that map points between different Torelli spaces using that forget and transform process?
Right, like morphing one constellation into another,
Yeah.
but with points.
Exactly. So what Hidalgo found is that when you use one of those functions to map points to a new arrangement, the coordinates of those new points, they can always be expressed as cross ratios of the original points.
Wait, hold on. So you're telling me that cross ratios, this thing I learned about in high school, is the key to understanding these really complex spaces?
It is pretty amazing, right? Like, who knew that something so simple could have these really profound implications in the most unexpected places?
This is wild. So what does it all mean? What are the broader implications of Hidalgo's work? What are mathematicians most excited about when it comes to these discoveries?
Well, for one, it gives us this whole new way to study and understand these really complex spaces.
Okay.
It's like opening up all these new avenues for research and exploration. For example, we can start asking, well, do similar structures exist in even higher dimensions? So instead of points on a plane, what if we were arranging shapes in some multi-dimensional space?
Now that sounds like something straight out of science fiction.
Right. But that's what's so cool about math. It lets us explore these ideas that push the boundaries of what we can even imagine.
Right.
Another really cool thing is that it could have applications in other fields. Think about physics, where you have configurations of points. They're important for describing everything from how particles behave to the large-scale structure of the universe. Who knows, maybe Hidalgo's work with these abstract spaces could end up having some very real-world implications.
Wow. So Hidalgo's work is kind of like a springboard that could launch us into a much deeper exploration of these mathematical concepts, these spaces, and their connection to the world around us.
Exactly. But, even beyond the applications and the research, I think Hidalgo's paper is a testament to the power of just pure mathematics, It's about uncovering these hidden patterns and this beauty in the universe, even in places where things might seem completely chaotic. And you know what I always say?
There's always more to learn.
Exactly. And in fact, Hidalgo ends his paper with this really thought-provoking question. What happens when these specific types of Torelli spaces become so complex that we can't even describe them with simple equations anymore? What does that tell us? What other tools do we need? What other perspectives might help us to understand them?
So it's like we've done this deep dive, we've come to the surface, but now we've got a whole new set of coordinates to explore this uncharted territory. This has been incredible. Thanks for joining us and being our guide today.
My pleasure.
And for all our listeners, we hope you enjoyed this deep dive. And until next time, keep those brains engaged.
All right, so get ready, because today we're going to be really diving deep into the world of Torelli spaces.
Sounds a little intimidating, right?
Maybe a little bit at first glance, but honestly, this mathematical paper we're looking at, it's got a really cool discovery tucked away in there, somewhere among all the, technical jargon.
It's true. It's amazing how even when you get to the really, really abstract parts of math, you can still find these really elegant concepts just waiting to be found.
Okay, so before we get too far ahead of ourselves, what exactly are Torelli spaces? I mean, for those of us who haven't spent much time in that particular corner of mathematics.
Well, imagine you've got a sphere, like a globe,
Okay, got it.
and you're putting points on it, kind of like stars on a night sky.
All right, I can picture that.
A Torelli space is basically a way to categorize all the different ways you could arrange those points.
So every different arrangement of stars, that's like a different point in this Torelli space.
Exactly. And the way mathematicians write it out is with this. U0, comma, k plus 1. Well, mathematicians. Anyway, it represents a Torelli space for arranging k plus 1 points on a sphere. But, and this is kind of a key point, it's not just about where those points are, it's also about the shape of the sphere itself. Like if you could squish that globe, those arrangements, they'd change, right?
Right.
So the Torelli space is kind of helping us make sense of all that mathematically.
Okay, that's pretty interesting. But this paper, it doesn't just describe these Torelli spaces, it focuses on what are called holomorphic maps. And if we're sticking with our our stargazing analogy, maybe we can think of them as like the routes between those different star arrangements.
I like that, the routes, yeah. And just like with actual roads, some of these holomorphic maps, they're pretty straightforward, and then you've got others that are much more complex.
And what makes these maps, these holomorphic maps, so special is that they're not just random paths between points in this Torelli space. They actually, they preserve the structure of those spaces.
That's a key point.
It's almost like, when you have a map projection, like you're taking a 3D globe and you're trying to flatten it into a 2D map, but you want to keep the continents recognizable.
Exactly. It's all about maintaining those relationships, those geometric relationships, even as we're moving between these arrangements.
So what this paper uncovers about these maps, it's actually surprisingly straightforward. They have to follow these very specific rules, almost like a knight in chess, I guess you could say.
It's a good way to put it. It's like there's a limited number of moves.
So like a rule book for navigating these Torelli spaces.
Yeah, basically. And the paper, it really zeroes in on this thing called Theorem 1. It's all about defining those specific moves or forms these maps can take.
Okay, so walk me through this. What are these rules?
Well, there were some pretty technical terms involved, like forgetful maps and let's see, the cross ratio. But trust me, they're really cool concepts once you kind of wrap your head around them.
All right, well, let's try to wrap our heads around them. What's a forgetful map?
Okay, so imagine you've got this incredibly detailed map. Covers the entire United States. But you only care about California, say. You might just zoom in on California, right? Effectively kind of forgetting about the rest of the map.
Okay, makes sense.
These forgetful maps, they work kind of like that. They let us zoom in on specific parts of our Torelli spaces. Ignore the rest, just to make things a little easier to analyze.
So if we were looking at, say, all the ways to arrange 10 points on a sphere, we could use a forgetful map to narrow things down, just focus on maybe 5 of those points.
You got it. And once we've zoomed in with our forgetful map, we can start looking at those points, see how they're positioned relative to each other using this thing called the cross ratio. And now the math behind it, that can get pretty hairy.
I bet.
But the important thing is what it does. It basically acts as this measuring stick, telling us how spread out or clustered together those points are.
So we've got these forgetful maps, right, helping us simplify things. And then we use this cross ratio to actually analyze the arrangements themselves. But how do those two things connect back to this rule book idea for our holomorphic maps?
Well, that's kind of the beauty of this paper, you see. It shows that any holomorphic map, right, between these Torelli spaces, it can be broken down into combinations of those two things, the forgetful maps and the cross ratios.
Interesting.
It's like, imagine you're on a grid, right, and you can only move north, south, or east, west.
Okay.
No diagonals, no teleporting, nothing like that. Those are the rules, those two moves.
I'm starting to see where you're going with this.
And it's the same with these maps. They have these very specific rules, these very specific moves that they have to follow.
So even though these Torelli spaces and these maps, they seem incredibly complex at first glance, there's this underlying simplicity to how they operate.
Exactly. Yeah. Got it. And that's actually why this is such a big deal, this discovery. Because by understanding this structure, this kind of hidden simplicity, it gives us this whole new way of looking at these mathematical concepts, a new lens to view them through, you could say.
Okay, I'm getting why you're so excited about this now, but I've got to ask, why should we care? I mean, we're not all mathematicians here. What's the broader significance of all of this?
Well, that's the great thing about math, isn't it? Even when it seems, completely abstract, totally out there, it often reveals these fundamental truths about everything, the world around us,
Okay, I can get on board with that.
And while this particular research is still, it's theoretical, it has the potential, and this is really exciting, I think, to impact fields beyond just pure mathematics. We could be talking computer science, even physics.
Okay, now those are some applications I can get behind. So what kind of real world impact did this research actually have? Give me some examples.
Sure. Well, think about information theory, for example.
Yeah.
Coding. Every time you download a song or stream a movie, you're relying on these complex algorithms that are encoding, decoding data.
Right. Makes sense.
And at the core of that, you've got these arrangements of, bits, essentially. And these arrangements, they've got a lot in common with what we're talking about with Torelli spaces.
Wait, so you're saying that by understanding the structure of these spaces and these rules, the rules governing those maps, we could actually find better, more efficient ways to store data to transmit information.
It's definitely a possibility. And it doesn't stop there. This stuff could even have applications in, say, computer graphics. You know, how we create realistic textures, surfaces in video games, animated movies.
Yeah.
Well, that requires some pretty intense mathematical modeling. And because Torelli spaces are all about, arrangements on surfaces, the insights from this paper, they could lead to some pretty big innovations in that area. It's all about seeing the connections.
It really is.
And sometimes those connections, they pop up in the most unexpected places.
So from like faster downloads to better graphics in video games, who knew abstract math could be so impactful, right?
And honestly, we've barely scratched the surface here. This research, it's still in its early stages.
Right.
But the potential, it's really huge. We could even see an impact in, like, cosmology.
Cosmology. Okay, now you've really lost me.
Think about it. Trying to understand, the distribution of galaxies in the universe, right?
Okay.
That's essentially a giant arrangement problem.
I guess, yeah, when you put it that way.
And the tools from this paper, the insights, they might give cosmologists a whole new way to analyze those structures.
It's kind of amazing to think that the same math used to, like, describe points on a sphere could unlock these huge cosmic secrets. This whole deep dive has really driven home that idea of, like, looking for those hidden patterns, the structures, even when things seem incredibly complex on the surface.
Exactly. It reminds me of that quote by, what was his name? Bertrand Russell,
Yeah.
The mathematician.
I think I know who you're talking about.
He said, mathematics, rightly viewed, possesses not only truth, but supreme beauty. Something like that, anyway.
I like that. Though sometimes I think you need a bit of a guide to help you see the beauty, to really appreciate it,
That's what we're here for.
That's what we're here for. All right. Well, I think we've definitely accomplished that today with our deep dive into, what were they called again?
Torelli spaces.
Right, Torelli spaces. Who knew something so abstract could be so, well, fascinating?
Makes you wonder what else is out there, huh?
It really does. And on that note, I'm going to leave our listeners with one final thought. What other surprising examples of, maybe we could call it hidden simplicity, are out there just waiting to be discovered? And what incredible things could those discoveries unlock? Think about that. And until next time, happy exploring.